Hey Phys1 kids, Mr. C here, and we're going to continue our conversation about how to represent motion visually through graphing. So this is part 2 of the video that we started a day ago. So to begin, where we kind of left off is with this whole idea of acceleration. We talked about this in class a little bit 2 days ago, and we talked about it again a little bit yesterday. Remember we mentioned that the slope of your velocity versus time graph is your acceleration. Well, in this class, we're only going to deal with constant acceleration. And there's only 3 types of constant acceleration. Our first type is constant zero acceleration, which means we're not accelerating at all. We just have a nice line at 0. We have constant positive acceleration, which is going to be a straight horizontal line at some positive number. And we have a constant negative acceleration, which means we're going to have a nice straight horizontal line and a negative acceleration. And all that means is that we're picking up speed either in the positive direction or the negative direction, or in the case of zero acceleration, we're not picking up speed at all. So what that means in very physicsy terms is if we have a constant zero acceleration, we have a constant velocity. It means we're not changing our velocity at all. We're just traveling along the same velocity, very happy, we're content. If we have a constant positive acceleration, that could mean one of two things. Either A, we're speeding up in the positive direction, or B, we're slowing down in the negative direction. So basically, if our position and our velocity have the same sign, we're going to have a positive acceleration. Constant negative acceleration is the opposite. If it means we're slowing down in the positive direction, so maybe we're driving our car and we slam on our brakes, or we're speeding up in the negative direction. So if our position and our displacement, or our if our position or velocity have different directions, that means we're going to have that negative acceleration. So speeding up and slowing down. Well, in order for an object to speed up, the velocity and acceleration must point in the same direction. So this means we can have a positive velocity and a positive acceleration, which will result in a positive slope and a positive concavity. So in this case, we have a positive slope of our velocity versus time graph. That means we have a positive acceleration, or our concavity here is positive. We're getting bigger and bigger and bigger. That means we're going to have a positive acceleration. Or we could have, and that means we're also speeding up. Or we could have a negative velocity and a negative acceleration, which results in a negative slope here and a negative concavity. That kind of looks like we're going down. That also means we're speeding up. So as long as our velocity and acceleration are pointing in the same direction, we're going to be speeding up. In order to slow down, we need our velocity and acceleration to point in opposite directions. So we either have a positive velocity and a negative acceleration, or we have a negative velocity and a positive acceleration. On the next slide, I'm going to talk a little bit more about how we can better recognize this, because sometimes we're only going to be given just the position versus time graph. And we're going to be asked, do we have a positive acceleration? Are we speeding up? What's happening? And we're going to have to infer a lot of information. Some tricks to do this is to look at what our graphs look like. If we have a graph that looks like a smiley face, that means we're going to have a positive concavity. So that would be a graph that maybe looks like this, or it could look like this. That's a positive concavity. It looks like a smiley face, which makes me happy. I'm going to draw 2 eyes here, maybe a nose, and he looks kind of evil, but he's smiling, so he's happy. If our curves look like a sad face, that means we have a negative concavity. So that might be something that looks like this. It looks like half of a sad face, or maybe it might even look something like that. That also looks like a sad face. That means we have a negative concavity, which means we have a negative acceleration. So smiley face, positive concavity, positive acceleration. Frowny face, which is sad. That means we have a negative concavity, which means we have a negative acceleration. And last but not least, we can't forget what happens. What happens if we have no concavity? So it's just a straight line? Well, that means our object has zero acceleration, which is our constant zero acceleration. Pretty cool, right? So now I want you to take a few seconds, pause the video, and I want you to try and determine Which of these graphs have a positive velocity and a negative velocity, are speeding up or slowing down, have a positive acceleration or have a negative acceleration? And some of these will have more than one answer. So go ahead and pause and see if you can get the correct answers. Well, I hope you guys did good, and I hope you guys got them right, but we'll talk about them real quick. So, number one, we want to look at what has a positive velocity. That means that our graph will have a positive slope. If we look carefully at A and B, we can see that they both have a positive slope. And although it is a curved line, if we were to draw a tangent line to any point, we see that the slope of that tangent line would be positive. Another way to look at that is we're increasing here. We're going up. We're getting steeper. We're positive in this case. That means we're going to have a positive velocity. If we look carefully at C and D, we can see that their tangent lines, if we were to draw tangent lines for them, would be negative. And we know that the slope of our position versus time graph, which in this case we can get from a tangent line, is the velocity. So if we have a negative slope, that means we have a negative velocity. Now speeding up and slowing down. Well, in order to speed up, our graph needs to get steeper. And it needs to either get steeper and steeper and steeper in the positive direction or steeper and steeper in the negative direction. And if we actually look at A, we can see that we get steeper and steeper in the positive direction. That means that we're speeding up. And if we wanted to kind of prove this, we could draw a whole bunch of different tangent lines, and we would see that the slope of each of those tangent lines at different points in times is going to have a bigger and bigger magnitude, which means we're speeding up. We can say the same thing with C. Even though it's our tangent line, our velocity is negative, it's still getting more and more negative, which means it's getting a bigger and bigger magnitude. And that means that we're also speeding up. It's just we're speeding up in the negative direction rather than speeding up in the positive direction. If we look at number 4, which ones are slowing down? Well, slowing down is the opposite of speeding up. That means we plateau as time goes on. We reach a point where we eventually, we're just like, eventually, our position's not changing at all. And if we look carefully at B and D, we can kind of see that plateau happening. As we come up, we get slower and slower, and we start plateauing here until eventually we just stop moving and we're stuck at 150 meters. D is the same. It goes down, 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 and slowly starts getting less steep until eventually it plateaus at 0. Another way you could do this is you could draw the tangent lines again. So if we draw tangent lines at B, we see that it gets less and less each time. That means that our velocity at each point in time is getting smaller and smaller and smaller. And if our velocity gets smaller as time goes on, that means we're slowing down. And finally, 5 and 6, these were hopefully the easier ones because we just talked about these. We want to know which ones have a positive acceleration. That means we want to know the curves that look like that smiley face. And in this case, that's going to be A and D. They look like the smiley face. In this case, A is our right half of the smiley face, so we'd have our right eye here and, I don't know, maybe part of a nose. And then D over here is our left half of the smiley face, so we'd have the rest of our nose over there. Number 6 is asking us which ones have a negative acceleration, and that's going to be those graphs that look like a frowny face, which in this case is C and B. They look like a frown. In this case, C is our right half, and D is the left, or B, sorry, B is the left half of our frown. Now, the next topic that we want to talk about that is important to us, because we've already talked about how slope is important in each of our graphs, the area under the graph is also important. So the area under a graph kind of shows what's being built up over time. And there's really 2 main equations that you're going to need to know. You're going to need to know the equation for the area of a rectangle, and you're going to need to know the equation for the area of a triangle. Now, we can see that any physics equation in this format of x times y, so, this might be x, this is y, x times y, we can use the area of a graph of those variables to find out what we want. So this might be kind of confusing. So let's say we rearrange our equation, velocity is equal to position or displacement over time. And we get that our displacement is equal to velocity divided by, or to velocity times time. Well, let's go back to our velocity versus time graph, and let's say we have a slope like this. Well, that all suddenly means now that the area under this curve, 1/2 base times height, is in this format of x times y, which means that the area under our velocity times time graph is actually going to be equal to our displacement. Pretty cool. So area under v versus t graph is equal to our displacement. So just to kind of recap, and sorry about these weird boxes, my Google Slides did not transfer well, but they're basically just vectors, showing that all these quantities are vectors. All of our position, our velocity, and our acceleration graphs are all connected. So if we kind of start with our position graph, we know that the slope of our position graph is our velocity, and the slope of our velocity graph is our acceleration, which is pretty cool. Another way that you can look at this if you know calculus is the derivative of our position graph will give you our velocity, and the derivative of the velocity graph will actually give you acceleration. But you don't need to know that for this class. All you need to know for this class is that the slope of our position graph gives us our velocity, and the slope of a velocity versus time graph can actually give us our acceleration. Another cool thing is the area under the curve. The area under the curve of our acceleration represents the change in velocity. So like, let's say if we're looking at our acceleration graph and we want to know what our change in velocity is from time 0 to time 2, let's say, well, we can just take the area under the curve, which is going to be equal to base times height, which in this case will be equal to 2 times 4, which is going to be 8, which means that time equals to 2 seconds, we should be at 8 meters per second. If we actually go down here to 2, we can trace it up, and we find that we are indeed at 8 meters per second. Pretty cool. And we can do that with any period in time. We also know now that the area underneath of a velocity versus time graph, which I kind of hinted at in our last video, is actually equal to our displacement, our change in displacement. So if we looked and we wanted to know how far we traveled in 0 and 5 seconds, we could just look at our velocity versus time graph and say, well, delta x is equal to v times t, which in this case is going to be equal to 20 times 5. But because it's the area under the curve, we have to do 1/2, 20 times 5. So it'll be 1/2 our velocity times time, 1/2 20 times 5, which is actually going to give us 15 meters. And if we go to our position versus time graph at 5 seconds, we find that we are indeed at 50 meters. Pretty nifty. This might come in handy one day. So now what I want you to do now, what we're going to do is we're going to calculate the area of each segment of motion for this velocity versus time. So the first segment of motion is between 0 and 2 seconds. Well, to calculate how far we've traveled, all we have to do is find the area under the curve, and that's just going to be base times height, which in this case will be 2 times -2. So our displacement in this case is just 2 times -2, which will be -4. And it's always important to remember your sign here, because in this case we have a negative velocity, which means we're moving in the negative direction. Between 2 and 4 seconds, we're traveling with 0 velocity, which means we actually haven't traveled at all. So our delta x, or our displacement, is going to be 0 meters. And finally, our last segment here, between 4 and 6 seconds, we have to find the area under the curve. We have a positive velocity, which means we're moving in the positive direction. And that means we have to take the area under the curve. So we're going to take 4, our area, our base is going to be 2 seconds, and our height is going to be 6 meters. So we do 2 times, or our height is 5 meters. So we're going to do 2 times 5, and we find out that our delta x for this segment is equal to 10 meters. Now we want to translate that information to an x versus t graph. So we want to find what our x versus t graph would look like. Well, in time 0 to 2 seconds, at 2 seconds, we were all at -4 meters, or we traveled -4 meters. So at 2 seconds, we were all the way at -4. And because we were at constant velocity before, because we had that straight line, we need to know that the slope of our graph, we need to have a linear slope. That means a linear slope means we have a constant velocity. Between 2 and 4 seconds, we traveled 0 meters, which is going to look something like this. We haven't traveled anywhere. And finally, between 4 and 6, we traveled 10 meters. So between 4 and 6, we went from -4 plus 10 will bring us all the way up to 6 meters. And we know that our displacement in this time period was 10 meters. And this is what our position versus time graph is going to look like for the previous velocity versus time graph. So now, what about this graph? Well, this one's a little bit different because we can't, the area, it's not a rectangle anymore. Now it's going to be a triangle. So we have to calculate basically what our position is at each time. So at 1 second, we would find the area under the curve, which will be this triangle here. So at 1 second, our position is going to be 1/2 1 times 1, which just gives us 1/2, and we can go ahead and plot that right here. At 2 seconds, we would do 1/2, 2 times 2, which is going to give us 2 meters. And then finally, at 3 seconds, we would find the area under the curve, and we find that our position at 3 seconds is 1/2, 3 times 3, which is going to give us around 4.5, which is way up here. And this actually gives us a curved line. So one thing to notice here is we have a positive velocity, right? We have positive velocity, and our velocity has a positive slope. So that means we have a positive acceleration. Well, if we go back down here and check out our position versus time graph, we see it looks like the smiley face, which also means a positive acceleration. So our graph does match up. That is the end of this video. We'll talk more about this stuff in class. Go ahead and answer your video check 3 for this video. Submit that along with any other questions, and I will see you in class to talk more about graphs and motion.